In this video, we're going to prove the following statement. That if S is a bounded subset of a metric space E, then for any point P and E in that metric space E, for any point P in that metric space E, we have that there exists a open or closed ball that contains S. Now, before we prove this, we're going to remind ourselves of the following definition. So, definition of bounded. So, a set S, a subset S of a metric space E is bounded if there exists some open ball, some open or closed ball that contains S. So let's prove our statement. Now that we have this definition about, let's prove what we want to prove. Okay, so we know that since S is bounded, so here, let me write proof here. S is bounded, so therefore that implies that there exists an open ball or closed ball, so we'll just say closed ball that contains S. And we'll call that closed ball B, and it has center, say, P naught, and it has radius R. So center P naught and radius R. So now, let's remind ourselves of what it means to be in a closed ball or an open ball. All right, in this case, let's remind ourselves what it means to be in a closed ball. So a closed ball, B, so B, in this case, B is equal to all the points A such that the distance, whatever this distance metric is defined for this particular metric space, so however we define this distance metric for this particular metric space, the distance between the center, P naught in our case, and A is less than or equal to the radius of that closed ball. Okay, so let's draw out what this situation, what's going on in this situation. So we have our center of our open ball or closed ball, P naught, and we have our set that's bounded. We'll draw it like this, and we have our open ball our closed ball that contains S. And here's S. And then this closed ball has radius R. And we want to show that given any point Q in our metric space E, there exists a closed ball with center Q or an open ball with center Q that contains our bounded set S. So let's do that. So for this proof, I'm only going to show that there exists a closed ball that contains there exists a closed ball that contains S, because if I can show that there exists a closed ball that contains S, then for any closed ball, there exists an open ball that contains it. I'll leave that proof to you. And we can also say, and I'll leave this proof to you as well, that for any open ball, there exists a closed ball that contains it. So I'll leave those proofs to you, and they're not too hard to prove. But so let's if we can show that there exists a closed ball for any point with center Q for any Q in our metric space E that contains our bounded set S, then we've proven what we wanted to prove. We've also shown that there exists any open ball that contains it, or there exists an open ball with center Q that contains S. So we know the following statement. So let Q be somewhere here. And we know that we want to show that there exists some closed ball like this that contains S. So we know the following statement. We know that the distance between Q to P naught plus the distance between P naught to A for any A in A is less than, or excuse me, is greater than or equal to the distance between Q and A. And we know this statement because of the triangle inequality. The distance between Q and P plus the distance between P and A is greater than or equal to the distance between Q and A. And this is due to the triangle inequality because we have a metric space E, and therefore that metric space satisfies all four properties of a metric space, which I've talked about extensively in other videos. So check those out if you have any questions about why we can make this statement. And we also know the following, we can also say the following statement. Since S is contained in, I meant to say here, this is supposed to be an S here, for all S, not an A, for all S and S, because remember, our bounded set is S, sorry about that, our bounded set is S, and for any S and S, the distance between Q and P plus the distance between P naught and S is greater than or equal to the distance between Q and S. The distance between Q and S. But look at this. We also know that since S, the set S, is contained in this open ball B with center P naught and radius R, that we know the following statement. Since that means that S satisfies being in this open ball. So therefore, we can say that the distance between P naught and S is less than or equal to R. Because for any S and S is contained in this open ball, so therefore any S and S is in this open ball, so therefore it satisfies the property of being in this, in this closed ball, so therefore it satisfies the property of being in this closed ball. Therefore the distance between the center and any S in our bounded set S, of which is that is contained in this closed ball, must be less than or equal to the radius of that closed ball. And we also know, and it might seem trivial why I'm writing this, but you'll see in a second why I am, the distance between Q and P naught is, of course, equal to the distance between Q and P naught. And why am I saying this? Because I'm gonna dredge up a great inequality property that I've used multiple times in these videos and that I love to use, because we can say the following. If A is strictly less than or equal to B, and C is less than or equal to D, then that implies together that A plus C is strictly less than or equal to B plus D. And that follows the proof for this property, as I've said extensively in other videos, that follows very nicely from the proof of this property, which I've proven in a separate video, that if A is strictly less than B and C is less than or equal to D, then that together implies that A plus C is strictly less than B plus D. The proof for this property follows very easily, the proof for this property, this implication right here, follows very easily from the proof for this implication here that I've proven in a separate video. Okay, we can say the following statement, which I'll write over here in purple. We can say that R, the distance R, just R, that number, which is the radius of our closed ball here, plus the distance between Q and P naught that distance is greater than or equal to, again, by directly applying this property that I've circled here in purple here, by directly applying, because R is greater than or equal to this, the distance between P and S, and the distance between Q and P naught is equal to the distance between Q and P naught. So therefore, R plus the distance between Q and P naught is greater than or equal to the distance between Q and P naught plus the distance between P naught and S. And look at this. This distance right here, is greater than or equal to, by the triangle inequality, because all metric spaces must satisfy the triangle inequality, and E, and with the metric D defined on it, is in fact a metric space. So therefore we can say that the distance between Q and S is greater than or equal to this guy, but this guy is greater than or equal to this guy. So therefore, look at this. The distance between Q and S is greater than or equal to R plus the distance between Q and P naught. So therefore, we can say the following: for any arbitrary, this inequality, it holds for any arbitrary S in our bounded set S. So therefore, we can say that S is contained, or more so, we can say that S is in the ball, the closed ball of center Q and radius R. R plus the distance between Q and P naught. And this is a weird notation. I don't know why I'm writing like this, but this closed ball is equal to all the points A, such that the distance between Q and A is less than our radius, which is R plus the distance between Q and P naught. And look at this. We have that S is less than or equal to. We have that S is less the distance between Q and S, the center of our arbitrary, or the center of our closed ball that we're wanting to contain our set S that is bounded. That distance between Q and S is in fact less than or equal to our radius that we're defining. So therefore, we have just found a closed ball that contains S and has center Q, where Q is an arbitrarily chosen point in our metric space E. And therefore, we're done. We've just shown this statement holds for any S in our bounded set S. So therefore, there exists a closed ball that contains S with center Q, where Q is any point in our metric space E. And we're done.